Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to discuss about the module Analog Ammeters and Voltmeters from the paper Measurements and Instrumentation. From this module, students will get to know about the following topic. First, we will study the analog ammeters and voltmeters. Next, we will study about the power loss in the ammeters and voltmeters. The classification of different types of instruments used as ammeters and voltmeters will be provided. Then, we will study the errors commonly present in these instruments. Finally, we will study the construction of the permanent magnetic moving coil instruments or PMMC. We will study in detail the various parts comprising its construction. Analog ammeters and voltmeters are classed together as there are no fundamental differences in their operating principles. The action of all ammeters and voltmeters, with the exception of electrostatic type of instruments, depends upon a deflecting torque produced by an electric current. In an ammeter, this torque is produced by current to be measured or by a definite fraction of it. In a voltmeter, this torque is produced by a current which is proportional to the voltage to be measured. Thus, all voltmeters and ammeters are essentially current measuring devices. The essential requirements of a measuring instrument are: first, that its introduction into the circuit where measurements are to be made does not alter the circuit conditions, which is very important. Second, the power consumed by them for their operation should be very small. Ammeters are connected in series in the circuit whose current is to be measured. Therefore, they should have a low electrical resistance. This is essential in order that they cause a small voltage drop and consequently absorb small power. Voltmeters are connected in parallel with the circuit whose voltage is to be measured. They should have a high electrical resistance. This is essential in order that the current drawn by them is small and consequently the power absorbed is small. So students, now let us first consider the power loss in the analog ammeters and voltmeters. Let Ra be the resistance of the ammeter and I be the current being measured. Power loss in ammeter Pa is given by I square multiplied by Ra watts. If Rv be the resistance of the voltmeter and V be the voltage being measured, the power loss in voltmeter is given by V square by Rv watts. Thus, in order that the power loss in instruments is small, the resistance of ammeters should be small and that of voltmeters should be large. Let us consider the types of instruments. The main types of instruments used as ammeters and voltmeters are: first, the permanent magnet moving coil, that is PMMC. Second is moving iron. Third is electrodynamometer. Fourth is hot wire. Fifth is thermocouple. Sixth, induction. Seventh, electrostatic. Eighth, rectifier. Of these, the permanent magnet moving coil type can be used for direct current measurements only, and the induction type for alternating current measurements only. The other types can be used with either direct or alternating current. The moving iron and moving coil types both depend for their action upon the magnetic effect of current. The former is the most generally used form of indicating instrument, as well as the cheapest. It can be used for either direct alternating current measurements and, if properly designed, is very accurate as well. The permanent magnet moving coil instrument is the most accurate type for direct current measurements, and instruments of this type are frequently constructed to have substandard accuracy. The electrodynamometer type of instruments are used both on AC as well as on DC. Their calibration for both DC and AC is the same, and hence they are very useful as transfer instruments. Thermal instruments have the advantage that their calibration is the same for both DC and AC. They are particularly suited for alternating current measurements, since their deflection depends directly upon the heating effect of the alternating current, that is, upon the RMS value of the current. Their readings are thus independent of the frequency or waveform of the current and of any stray magnetic fields which may exist in their vicinity. As voltmeters, electrostatic instruments have the advantage that their power consumption is exceedingly small. They can be made to cover a large range of voltage and can be constructed to have substandard accuracy. Their main disadvantage is that the electrostatic principle is only directly applicable to voltage measurements. The induction principle is more generally used for watt-hour meters than for ammeters and voltmeters, owing to the comparatively high cost and inaccuracy of induction instruments of the latter types. Students, now let us see the errors in the ammeters and voltmeters. There are certain errors which occur in most types of instruments, while other errors occur only in those of particular type. Of the errors common to most type of instruments, friction and temperature errors are perhaps the most important. To reduce the effect of friction torque and consequently the error produced by it, the weight of the moving system must be made as small as possible compared with the operating force. That is, the ratio of torque to weight must be large, about 1/10 for full deflection. A vertical spindle is generally preferred to a horizontal one from the point of view of a small frictional torque. The most serious error is produced by the heat generated in the instrument or by changes in ambient room temperature. Is that due to a change in the resistance of the working coil? Such a change of resistance is of little importance in ammeters, but in voltmeters, in which the working current should be directly proportional to the applied voltage, it is essential that the resistance of the instrument remains as nearly constant as possible. Thus, the power loss in the instrument should be small and resistance coils which are likely to produce appreciable heating should be mounted if possible in such a position that they are well ventilated. In order to eliminate temperature errors, the working coil is wound with copper wire and is of comparatively low resistance. A high swamping resistance of material whose resistance temperature coefficient is small is connected in series with the coil so that although the resistance of the coil may change considerably, the change in total resistance is small. Other errors resulting from heating may be caused by expansion of the control spring or of other parts of the instrument. Although such errors are usually small. Lack of balance in the moving system and changes in the strength of permanent magnets, if used, are other possible sources of error, which are common to several types of instruments. So, students, now we will discuss the special case of permanent magnet moving coil instruments or PMMC in short. The permanent magnet moving coil instrument is the most accurate type for DC measurements. The working principle of these instruments is the same as the D'Arsonval type of galvanometer. The difference being that a direct reading instrument is provided with a pointer and a scale. We will discuss Now, in detail, the construction of PMMC instruments. The general constructional features of this instrument are shown in the figure. Students, now let us consider the moving coil. The moving coil is wound with many turns or enameled or silk covered copper wire. The coil is mounted on a rectangular aluminum former which is pivoted on jeweled bearings. The coils move freely in the field of a permanent magnet. Most voltmeter coils are wound on metal frames to provide the required electromagnetic damping. Most ammeter coils, however, are wound on non-magnetic formers because coil turns are effectively shorted by the ammeter shunt. The coil itself, therefore, provides electromagnetic damping. Next is the magnet systems. There has been considerable development in materials for permanent magnets, and therefore magnet assemblies have undergone a lot or change in the recent past. Old style magnet systems consisted of a relatively long U-shaped permanent magnet having soft iron pole pieces. Owing to development of materials like Alcomax and Alvico, which have a high coercive force, it is possible to use smaller magnet lengths and high field intensities. Thus, in small instruments, it is possible to use a small coil having small number of turns, and hence a reduction in volume is achieved. Alternatively, in instruments having a large scale length, it is possible to increase the air gap length to accommodate large number of turns. Students, next feature of the PMMC is the control. When the coil is supported between jewel bearings, the control torque is provided by two phosphor bronze hair springs. These springs also serve to lead current in and out of the coil. The control torque is provided by the ribbon suspension. This method is comparatively new and is claimed to be advantageous as it eliminates bearing friction. Next is the damping. Damping torque is produced by movement of the aluminum former moving in the magnetic field of the permanent magnet. Next feature is the pointer and scale. The pointer is carried by the spindle and moves over a graduated scale. The pointer is of lightweight construction and, apart from those used in some inexpensive instruments, has the section over the scale twisted to form a fine blade. This helps to reduce parallax errors in the reading of the scale. In many instruments, such errors may be reduced further by careful alignment of the pointer blade and its reflection in the mirror adjacent to the scale. The weight of the instrument is normally counterbalanced by weights situated diametrically opposite and rigidly connected to it. Now, let us consider the torque equation. The torque for a moving coil instrument is given by deflection torque is Td is equal to Nbi dl, which is equal to Gi, where G is a constant which is equal to Nbid. The spring control provides a restoring torque Tc equal to k theta, where k is the spring constant. For finally steady state deflection, Tc is equal to Td or Gi is equal to k theta. Therefore, final steady state deflection is given by theta is equal to Gi by k, or current I is equal to Ki theta, where Ki is equal to k by G, which is a constant. Next is the shape of scale. As the deflection is directly proportional to the current passing through the meter, we get a uniform or linear scale for the instrument. Next is the nonlinear scales. The conventional permanent magnet moving coil mechanism uses a core and pole pieces having concentric faces. This means that the field is uniform and radial throughout the air gap. When the current being measured is directly passed through the meter, the instrument shows a uniform scale. Now students, we will study the range of the DC ammeter and DC voltmeter. First of all, the range for DC ammeters. First, for the instrument alone, the range may vary from 0 to 5 microampere to 0 to 20 milliamperes. Second, with internal shunts, the range may vary up to 0 to 200 amperes. Third, with external shunts, the range may vary from 0 to 5000 amperes. Now, for DC voltmeters. For instrument alone, the range may vary from 0 to 50 or 0 to 100 millivolts. With series resistance, the range can be varying from 20,000 to 30,000 volts. In microammeters and low range milliammeters up to about 20 milliamperes, the entire current to be measured is sent through the moving coil. This is because the instrument springs serve as current leads to the moving coil. Their current carrying capacity limits the current which can be safely carried to about 20 milliamperes. For higher currents, usually above 20 milliampere, the moving coil is shunted to bypass current around the coil and the spring. It may be mentioned here that ammeters of range lower than 25 microamperes are not likely to be robust, on account of extremely delicate construction required for proper sensitivity. Thus, instruments of range lower than 25 microampere are normally not manufactured. Voltmeters or all ranges use a moving coil together with sufficient series resistance known as multiplier to limit the instrument current to the desired value. DC ammeters are normally designed to have a voltage drop of nearly 50 millivolt to 100 millivolt for full-scale deflection. Most DC voltmeters are designed to produce full-scale deflection with a current of 10, 5 or 1 milliampere. Normally a value of 1 milliampere is used. Thus, excluding low-range current measuring instruments, most DC ammeters are actually 50 millivolt or 100 millivolts operated with a suitable shunt, while voltmeters are low-range milliammeters operated with a suitable series resistance. So students, let us summarize what we have learned in this module. We learned about the analog ammeters and voltmeters. We saw that the essential requirements of a measuring instrument are: first, that its introduction into the circuit where measurements are to be made does not alter the circuit conditions. Second, the power consumed by them for their operation should be small. We learned about the power loss in the ammeters and voltmeters. We have classified the different types of instruments used for ammeters and voltmeters. We also studied about the common errors in these instruments. Of the common errors, the most common are the friction and temperature errors, and these are very important as well. We also studied the permanent magnet moving coil instruments, that is PMMC. We studied its construction comprising of various parts. The various parts present in the PMMC, which we studied in detail, were moving coil, magnet systems, control, damping, pointer and scale, torque equation, shape of scale, nonlinear scales. And towards the end, we read about the range of the DC ammeter and DC voltmeters. Thank you.